So for number 10, or assignment 10, number 1, part B, I forgot to calculate a new REQ. So with the switch closed, now the two bulbs are in parallel. So you have to add those 1 over the resistance of bulb A plus 1 over the resistance of bulb B equals 1 over the resistance of both of those. Um, and then that's in series with the resistance of the battery. So you have to add those together in series to get an REQ of 3.5 ohms. And then you use V equals IR to get the equivalent current. And then because to get just the current through bulb A, since the resistances of both the bulbs are the same, you divide the total current out of the battery by 2 to get 0.2143 amps. For assignment 8, number 4, making an SR flip-flop out of NAND gates, I originally had the S and the R switched on my truth table. So when S is 0, it sets Q to 1, and when R is 0, it resets Q to 0. So instead of with the NOR gates where 1 S sets it to 1 and 1 has R set it to 0, this time 0 sets and resets. Which makes our truth table, when they're both 0, it's unstable. When R is 1, Q is 1, and Q naught is 0. And when S is 1, Q is 0, and Q naught is 1. And when they're both 1, it just resets to whatever it was before. So for number 2 on assignment 13, first you plug in V naught e to the JWT for V, and V naught over the magnitude of the impedance, or Z, e to the JWT minus theta. The star means the complex conjugate, which means take the negative of the exponent. Then I split up my exponents into, from the current into e to the JWT times e to the negative j theta. And then because you've got e to the JWT and e to the negative JWT, those can cancel, which leaves you with this. And then because then you split up the e to the negative j theta into cosine of theta minus j sine theta. And then because you only want the real part, the j sine theta disappears, and you end with power equals V naught squared over 2 times the magnitude of the impedance times the cosine of theta. So for assignment 13, number 3, the impedance of the capacitor ZC is negative 6J. It's in the imaginary frame. So VR, you're going to have a vector combination of real and imaginary numbers, 2 ohms minus 6J ohms. Then using the Pythagorean theorem, we can find the magnitude of that vector and thus find the magnitude of the voltage to be 2.539 volts across the resistor. Then for the capacitor, use the Pythagorean theorem again, and you find the magnitude of the voltage to be 7.589 volts. For assignment 13, number 4, we're looking for the equivalent impedance between point A and point B. So first I labeled each of them Z1 through Z6, and then wrote those out in terms of either capacitance, inductance, or resistance. Then I tackled the 3 in parallel. I labeled that ZA. And so 1 over ZA equals 1 over negative J over WC2, which is Z4, plus 1 over negative JWC3, which is Z5, and plus 1 over JWL2, which is Z6. And through all of the math, ZA comes out to equal 2000J. Then to get the total Z equivalent, you add Z1, Z2, Z3, and ZA in series, which becomes R plus a negative J over WC1 plus JWL1 plus 2000J, which becomes 4,000 minus 2000J plus 6,000J plus 2000J, which Z equivalent becomes 4,000 ohms plus 6,000 J ohms.